Hello, my name is Kyle Brinker, aka Mr. B, and today we're going to be talking about a topic involving abstract algebra, and that is Sicherman Dice. This is a fun look at probabilities and looking at like standard dice and unique dice, and it'll just be a fun project. So let's take a look. So what am I going to be talking about today? Today I'm going to be looking at the historical background of Sicherman die, and then we're going to be looking at an introduction to the problem, looking a little visual aspects of it. Then we're going to go into the solution and reasoning. Why does this work? We're going to talk a little bit about the proof of why it works. And then finally, we're going to allow blank faces for the dice and see what happens. So that's our agenda for today. Let's get started. So let's talk a little bit of background about Sicherman dice. Well, Sicherman dice was first proposed by Martin Gardner in the Scientific American issue that was published in 1978. He claimed that if you have a cube, a die with faces with values of 1, 2, 2, 3, 3, 4, and a second cube with faces 1, 3, 4, 5, 6, and 8, then the probability of rolling a particular sum is identical to the probability of rolling that same sum with a pair of ordinary dice, which is absolutely mind-boggling, which what brought me into this project. Gardner called these special dice Sicherman dice, named after Colonel Sicherman. So let's give a little introduction into it, and we're just going to look at things visual right now before we dive into the reasoning and the proof aspect of it. So on the left-hand side here, I have all the possible outcomes when rolling a standard pair of dice. So we have only one possibility for 2, 2 possibilities for 3, 3 possibilities for 4, 4 possibilities for 5, 5 possibilities for 6, and so on. And now when we look over here on the right, we have the proposed Sicherman dice, and I'm not going to, if you want to take a pause to pause the video and verify it yourself, but I can tell you right now that for each sum, there is the same number of possibilities as rolling 2 standard dice. So when we create the table, they definitely do come out to be the same. But let's dive a little deeper, see what we can figure out from an abstract point of view. So why does this work? So let's consider the product of two polynomials where the values of the faces of an ordinary die is represented as exponents. And we have a pair of dice here. So we have x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x squared, and x. And those are all added together. And we have those faces, 6, 5. And since we have a pair of dice, we're going to multiply it by the same expression, the same polynomial. And I'll explain why we set it up this way in a minute. But let us also consider how we obtain a particular sum. Let that be 5 in this case. So we can, when I roll a standard pair of dice, I can get 5 in 4 possible outcomes. 4 in 1, 3 and 2, 2 and 3, 1 and 4. Notice how we can create this term x to the fifth, or this where the sum is 5 up there in the exponent, in these ways. There's 4 ways. 4 and 1, 3 and 2, 2 and 3, 1 and 4. There's this one-to-one correspondence they have. Now back to why we set it up like this. Well, when we multiply it out and do all the math to get just one giant expression, we actually get the probability distribution for a standard pair of dice. So we have one possibility for getting a sum of 2. We have 2 possibilities for getting a sum of 3. We have 3 possibilities for getting a sum of 4. And this pattern continues just like the regular probability distribution of rolling that standard pair of dice. Which is really cool because now we have a new way of looking at the probability distribution that we can use in our proof instead of looking at the a typical way of looking at probability distribution with a histogram. So this is extremely fascinating stuff. It's what brought me into the project, is looking at this probability distribution and seeing where it goes. So let's see where this goes. So now let a sub 1, a sub 2, a sub 3, all the way up to a sub 6, and b1, b2, up through b through 6, be lists of positive integers. So they're all going to be greater than 0. Let them be the values of the faces of a pair of dice such that they have the same probability as rolling any particular sum as with the standard die. So we're going to set this up, these 2 polynomials, into an equation. We're going to have the 2 dice on the left-hand side, and we're going to have the 2 new dice that we don't know the face values for yet on the right-hand side. So let's look at the left side first. Well, it turns out we can uniquely factor each die into the product of irreducibles x times x plus 1 times x squared plus x plus 1 times x squared minus x plus 1. So when we have a pair of dice, we have x squared times x plus 1 squared times x squared plus x plus 1 squared times x squared minus x plus 1 squared. So, by the unique factorization theorem, or theorem 3.2.8, in an introduction to abstract algebra with notes to the teacher, one of the new die we have is p to the x is equal to the polynomial x to the a sub 1, and adding all those terms up to x to the a to the 6. And that's going to be equal to x times q, or x to the q power times x plus 1 to the r power times x squared plus x plus 1 to the t power times x squared minus x plus 1 to the u power. And again, I want to emphasize this is just for one die. And these exponents will be between 0 and 2 and can include 0 or 2. In the end, if we want the same probability distribution, we need, for a pair of dice, the 2 q's to add up to 2, we need the 2 r's to add up to 2, the 2 t's to add up to 2, and the 2 u's to add up to 2. Now this is a lot of mathematical work that would take a lot of time to look at, so I want to find a way to make my life easier. And how can I do that? Well, let's take a look at restricting some of the parameters a little bit. So let's take a look at r and t. So let's assume x is equal to 1. So we're going to input that or substitute it into our polynomial. we're going to look at it two ways. We're going to look at the sum of all the terms. So 1 to the a to the 6th power plus 1 to the a to the 5th, all the way up to 1 to the a to the 1st. And that's, since anything 1 to any power is just 1, that'll sum to 6. Let's look at it with our unique factorization here. We're going to input 1, so we have 1 to the q power times 2 to the r power times 3 to the t power times 1 to the u power. And we want that to be equal to 6 again. And the only way that's possible is if r and t both equal 1. So r and t must both equal to 1. What about looking at q? So I'm going to claim that q cannot equal 2. And the reason for that is say we input q into our unique factorization here. The lowest term we're going to get is x squared. When we distributed all the terms out, x squared will be the smallest term. This represents a value of 2 on the die, and that will be the smallest value. That means that the other die would have to have a 0 because we need some way to get a sum of 2, since that is a possibility for a standard pair of die. We need to have it in this new pair of dice. But if we have 2 on 1 as the lowest term, then the other one has to have a 0 on it. And since we're not allowing any blank faces, all the faces have to be greater than 0. This cannot be a possibility. And since we're going to be eventually looking at a pair of dice, q cannot equal 0, because if q is equal to 2 for one of the die, then the other one would be q equal to 0, which is not possible since q cannot equal 2. So here's our possibilities now. We have q equal to 1, r is equal to t, which is equal to 1, and u can be 0, 1, or 2. And we're just going to substitute this into our unique factorization that we found. Let's do an example here. Let's say u equals 0. Then I've inputted 1 for q, 1 for r, 1 for t, and 0 for u. We can simplify this a little bit by having this factor here just be 1, because anything to the 0th power is just 1. So now when we distribute all the terms out and multiply everything, we get x to the 4th plus 2x cubed plus 2x squared plus x. And what does this mean? Well, we have one side with a value of 4, two sides with a value of 3, two sides with a value of 2, and one side with a value of 1. So this gives us labels of 4, 3, 3, 2, 2, and 1. But what about the other terms, u equal to 1, u equal to 2? Well, for u equals to 1, we get 6, 5, 4, 3, 2, and 1. And we get for u equal to 2, 8, 6, 5, 4, 3, and 1. So since if we roll a pair of dice, then u equal to 1, those are the two dice. That's the standard dice. And then we roll the u equal to 2 die with the u equal to 0 die. And those two together give us the same probability as rolling the two u equal to 1 dice, or the standard dice, in other words. So u equal to 0 and u equal to 2 die form a pair. And two u equal to 1 dice also form a pair, which is just standard die. But now, what if we allow for blank faces? So again, we're going to use that unique factorization. P of x is equal to x to the q times x plus 1 to the r times x squared plus x plus 1 to the t times x squared minus x plus 1 to the u. And again, I'm going to look at trying to restrict some of my parameters as much as possible. So by similar arguments as before, I'm going to say r is equal to t equal to 1. Nothing changes there. Everything's good to go. But now let's look at what q can be again. So as I said before, when we're allowing only positive integers for our face values and they all have to be greater than 0, we said we couldn't have a smallest value of 2 on one die and still have the same probability distribution with the pair of die, because the other die would have to have 0, which was a contradiction. But now we're allowing blank faces, so that possibility opens up, and we can now let q equal to 2. And similarly, we can also let q equal to 0 as well. And as before, u equals 0, u equals to 1, and u equals to 2. So let's go through an example calculation. Let q equal 2 and u equals 0. So substituting that into our unique factorization, we put q equal to 2, r equal to 1, t equal to 1, and u equal to 0. And again, we can simplify that down to 1. For anything to the 0th power is 1. And when we distribute out and multiply everything, we get x to the 5th plus 2x to the 4th plus 2x cubed plus x squared. So that means we have one face with a value of 5, two faces with a value of 4, two faces with a value of 3, and one face with a value of 2. So we have labels 5, 4, 4, 3, 3, 2 for one of the die. So what are the others? Well, for q equal to 2 and u equal to 2, we get labels 9, 7, 6, 5, 4, 2. For q equal to 2 and u equal to 1, we get 7, 6, 5, 4, 3, 2. For q equal to 2 and u equal to 0, we get labels 5, 4, 4, 3, 3, 2. For q equal to 0 and u equal to 2, we get labels 7, 5, 4, 3, 2, 0. Q equals 0 and u equal to 1, we get 5, 4, 3, 2, 1, 0. And q equal to 1 and u equal to 1, we get 3, 2, 2, 1, 1, 0. And this just adds on to the possibilities we already have. It doesn't replace them. It just adds on to it. So we have three new pairs out of this. We have 9, 7, 6, 5, 4, 2 and 3, 2, 2, 1, 1, 0. 9, 7, 6, 5, 4, 3, 2 and 5, 4, 3, 2, 1, 0. And 5, 4, 4, 3, 3, 2 and 7, 5, 4, 3, 2, 0. And you can roll any one of those new pairs, and you'll have the same probability distribution as rolling a standard pair of die. So here's the references I used. I hope you enjoyed this presentation. Take care now.